Good morning. Thank you for coming, staying for Science Sunday. So this morning we have a talk on Who's Afraid of AI, all about AI, from Steve Conn, who is an information technology professional. He's worked for 40 years as a consultant for clients in government, higher education, and healthcare. He's currently a Linux and cloud specialist working at National Institute of Standards and Technology. Please welcome. Oh, if you have questions, wait for the microphone, or if I don't repeat them, because it's going to be on Zoom, so you can also watch it again later if you want to. Okay, please welcome Steve Conn.
Thank you. I think, I'm trying to think back the last time, it's probably been 10 years, I think, or 8 years at least, since I've talked to a group of people who weren't in little boxes on my computer screen, actual people. And my first thought as I got up here was to look down and make sure I was wearing pants. I was asked to make this a non-technical talk, and when I thought about that request, and if I were, so my official job title, where I work at the National Institute of Standards and Technology, is I am a cloud DevSecOps architect, right? That's a mouthful of a title. And I thought if I had to lecture about what it is I do when I'm sitting at my desk at work or at home, it would, at worst, would make no sense whatsoever to most people who aren't within that specialty. And at best, it would be fabulously boring. So I thought, but approaching the topic of AI, it's very easy to talk about it in a non-technical way, because in a way, the main thrust of AI is something that you all do, for lack of a better term, without thinking about it. Human thought, human thinking, human cognition. I mean, these are all concepts we're familiar with, and we all have from the science courses we've taken in high school, have a basic understanding of what a brain looks like, how it works, and what thinking is, and we understand at least at a visceral level what consciousness is. So a lot of the things that AI wants to talk about are very familiar concepts to us, and luckily it's one of those cases where the underlying mechanisms of AI are extremely simple. But sometimes when you take extremely simple things and multiply them to millions, maybe billions, or even trillions of simple things, highly complex and interesting behaviors can emerge out of the activities of these very simple things. And that, in a lot of ways, is you'll see as I continue in my talk, is really the foundation of how artificial intelligence works. So I felt I had absolutely no problem really giving a largely non-technical talk about this subject. Michael gave me a brief introduction. There's a point in the movie Wall Street where Bud Fox, who's played by Charlie Sheen, finds himself in the office of his idol for 5 minutes. His idol is Gordon Gekko, the Wall Street financier and mogul and corporate raider. And at one point, early in the conversation, Gordon Gekko turns to him and says, "Why am I listening to you?" And so I thought I'd take just a minute and elaborate a little bit more on why you're listening to me. I'm not an AI expert, and nor do I really work in AI, so to speak. I have been an information technology professional for most of my life. I wrote my first computer program at 14, which these days would be not much of anything to say, but that was in 1973, when we didn't all have computers on our desktops or laptops. I've been involved in computers in one way or another. I didn't study computer science in college. I studied philosophy as an undergraduate, but through philosophy is how I initially got interested in AI and computational linguistics. So it's something that's been a kind of professional interest or personal interest of mine for a long time. And while my work life as a computing professional has not really ever revolved around artificial intelligence, so to speak, it's something that I followed with great interest for a long time. And I am a daily user of artificial intelligence in my work. In the software development field in particular, if you're not an active user of AI, you're going to find yourself behind the eight ball fairly soon. I'll say that maybe the best way to describe the influence AI has had in my day-to-day professional life is that I now spend a lot more time thinking about what it is I want to accomplish and a lot less time about how I'm actually go about accomplishing it. So AI is for me sort of like a pretty good assistant who never complains when I don't give it time off. I still do most of the work and the thinking, but a lot of the little fussy details of writing computer code and things like that, the AI is sort of an assistant in helping me. And so I would say that probably not a day goes by in my working life where I don't use AI in one shape or another during my work. So what we talk about when we talk about AI, I stole the idea for the title of this, excuse me, from a story written by Raymond Carver back in the 1970s. And in the story, two couples who are friends, sit around a suburban dining room table in the waning hours of the afternoon with a bottle of gin on the table between them, and they begin to talk about what love means. And in the course of the conversation, they disagree and they argue over whether love is a good thing or whether it's a bad thing, whether it's a good influence or a bad influence, whether it's supportive or whether it's destructive, and they relate this back to experiences in their own lives. One of the women in the conversation has had a very abusive husband who she still felt that she loves, and she feels she needs to explain that. And as the conversation goes on and the light dwindles and the evening comes on, they find themselves not ever really agreeing that they've defined it, but I think realizing that while there is one thing that's sort of at the base of everything they're talking about, it really is something. It's something that manifests itself in very different ways under certain circumstances and to different people. And I thought the same thing could be said about AI. We see the terms artificial intelligence and AI all around us now. It's almost kind of dizzying to me how, and we'll talk a little bit about the history of AI in a minute, but how AI has gone from sort of a niche academic interest to kind of a popular science fiction theme to maybe 3 or 4 years ago, and suddenly it burst in on us as something that was actually happening. We'll talk about this later on, but little pieces of the AI puzzle have actually been coming together for a long time. And a lot of the things that make what we see as AI, most publicly see as AI now, a lot of the technologies and ideas that make that possible really have been a part of our lives for a long time. They've really kind of come together in the last few years in a way and have found broad reach into our culture in a way that I certainly never would have predicted 3 or 4 years ago. So let's start with a little bit of history. I just pressed the center button? The side button to advance it? Okay. So the idea of making inanimate matter, a machine, think, or whether a machine or something non-human would be capable of thought actually goes a long ways back. And it strikes kind of at the root of what it is that differentiates life from non-life and what differentiates human life from non-human life. And the questions around those things have always been, is thinking something that's uniquely human? Is it something that's uniquely biological? Is it something that can be programmed into a device, a machine, or a mechanism? And oftentimes, for a lot of history, those ideas or those questions have been tied up in trying to come to understanding of what it is that thought actually is. And what does it mean to think? What does it mean to be conscious? What does it mean? And it's in the early part, in the first third, I guess in 1950, a British mathematician, Alan Turing, I'm sure that many of you have seen or at least heard about the movie The Imitation Game, that he was a cryptographer who was able to, he and his team at Bletchley Park were able to allow the Allies during the Second World War to decrypt the encrypted German submarine signals and thereby take an upper hand in the war against the German submarines. But he also had kind of a lifelong interest in computing as a mathematical activity, but also the idea of computing as a basis or an analog of human thought. And in 1950, he published a paper called Computing Machinery and Intelligence, where he starts out by saying, you know, many of the discussions of this sort of have gotten tied up in trying to define what thought is. So let's say we take a different approach to it. Let's say instead of trying to define what thought is, would it be equivalent, or nearly equivalent, to be able to define what intelligence looks like, or what thought looks like? And could you create a test that would allow you to answer the question, does X think, or is X capable of thought, whatever X may happen to be? And the idea he came up with was based on a psychological exercise called the imitation game, in which a person attempted, you had two people in different rooms talking only over a microphone or over a teletype. And the person in one room was tasked to determine whether the person at the other end of the microphone or teletype was a woman or a man. And Turing took this idea and said, well, could we do the same thing with a computer? So the imitation game, or the Turing test, I think as we now tend to think of it in the Turing test, was something he suggested as a way of answering the question, can a computer think? And so he's rephrasing it as the question, can we make a computer seem like it thinks? So again, his idea was put the computer in one room, put a person in the other room. He insisted using a teletype because back then speech synthesis was not an option. So obviously you couldn't carry on a kind of a vocal conversation. And he suggested that if you could convince a normal person that the computer responding on the other side, if the person could distinguish whether or not, or could not distinguish whether or not the person producing the text on the other side was a computer or a person, that you would have achieved something that appeared to be like a thinking machine. So fast forward to 1956. You know, one of the probably the biggest limit on the research that might have followed up on some of what Turing talked about was the primitive state of computing machinery at the time that he did it, that he wrote the paper. Back then, there weren't even really computers in the sense that we understand them now. But in the time between 1950 and 1956, early computers, you know, early digital computers had become available, and the capabilities and the potential of those computers to do complex computations had become apparent. So in 1956, they're kind of considered the fathers of AI, Claude Shannon, John McCarthy, Nathan Rochester, and Marvin Minsky, got together and convened the Dartmouth Summer Research Project on Artificial Intelligence. And what it really was like a 3 to 6 week brainstorming session. They brought other people in, other mathematicians, physicists, computer science, all trying to come up with ideas for how we might try to make machines think. In fact, the term artificial intelligence was coined during that session. And it's interesting that there was kind of a debate going back and forth between John McCarthy, who coined the term artificial intelligence, and Marvin Minsky, who preferred the term machine intelligence. And I think that Minsky's fear was by hearing artificial intelligence, once the word got out into the popular discourse, his fear was that people would think that by artificial we were suggesting something that would replace human intelligence. Whereas Minsky felt that the term machine intelligence would make it clear that they were talking about something that a machine would do, and that people wouldn't assume that we were attempting to replace human intelligence with machine intelligence. It's interesting, they were extremely optimistic at that. In the final paper, they predicted that machine translation of human language in a few years, so this would be before 1960. And they predicted artificial general intelligence, and we'll talk a little bit more about that later, but by which we mean a an artificial intelligence that's more than just an expert in a particular area, but that can reason about things about the world in general in the way a human does. But they predicted that we would have artificial general intelligence by the 1970s. Two pretty breathtaking predictions, and while they were certainly off, they weren't wrong in the end. So the, excuse me. So the paper that came out of this conference was created a lot of buzz around these ideas and a lot of excitement about some of the research, about the research that would come. But one of the prevailing issues that they would run up against over the next 20 to 30 years was the ability of computing machinery to do the kinds of things, do the kinds of things that they would need to be able to do in order to produce some proofs of concept. And in fact, computing machinery wouldn't really catch up to the way the artificial intelligence, as we're doing it now, wouldn't even really begin to catch up with the ability to do those things until probably 40 years later. In fact, they refer to the period from 1956 into the into the mid to late 70s as the AI winter, in the sense that there were a lot of papers written, a lot of concepts people came up with, but not a lot of actual working examples, simply because the capability of computing machinery wasn't there at the time. So I want to talk about the two kind of main forks of artificial intelligence research that emerged out of the work that McCarthy and Minsky and their crew had done. And this, obviously, for any of you who are familiar with this stuff, is a gross oversimplification, but I think it works in a lot of ways, and it kind of it feeds nicely in the discussion of the kinds of AI technologies that are in broad use now. But in a sense, there were kind of two general approaches to implementing artificial intelligence. And I kind of call it the mind versus the brain, right? There are two ways to think about thinking. One is to think about how we think. In other words, the conscious processes that we ourselves can reflect on as we try to think through a problem or think through a concept or imagine something. And those are kind of the province of psychology, right? Where in psychology, what we're trying to do is understand how the brain functions by observing and trying to understand human behavior. On the flip side of that is neurobiology, which seeks to understand thinking by understanding the actual mechanisms and processes, chemical and electrical, of the brain itself. And one of the really interesting and kind of exciting phenomena of the last 30 or 40 years has been the gradual meeting in the middle of what I call the psychological approach and the neurobiology approach. Psychology and neuroscience have been coming closer and closer and closer to the center, where we're getting closer to the point where neurobiology is able to relate directly to things that relate directly back to the phenomena that occur at the kind of conscious mind level, which is more normally the province of psychology. So in AI too, in the psychological or the cognitive, they also call this cognitive psychology, the cognitive approach to it. What they would do is to write software that they thought mimicked the way we actually think about these things. So software might mimic deductive reasoning, or there was a program called Sherdloo, which modeled basically an arm going into a room full of shapes, and it would take orders on what shapes to fetch. And if you look through the code, what the code is really doing is at sort of a micro level what you your own self do in your brain when you do that. So the computer code was based on trying to understand the actual conscious mechanisms or lightly subconscious mechanisms that go into human thinking and language production. On the other side, the neurobiology side, neural networks, which emerged in the 1940s and 1950s as well, where they actually tried to model networks of neurons, similar to the networks of neurons in the brain, and then use those to try and train those to try to do, to try to perform tasks. And we'll talk more about that later too. But there was this sort of split And most of the, if there were successes in AI that occurred in the 60s and 70s, virtually all of them were on the psychology, the mind side. Mostly all of those were things where people had programmed computers by modeling the way they thought worked. But at the same time, because neural networks had applicability in several areas of science, those continued to progress along the way, but I think they were much more under the radar than the more popularly visible AI work that was being done on the kind of cognitive or psychology side of the field. But all along, and I would also say too that the neurobiology approach or the neural networks approach also proceeded slowly because the computing resources that you need in order to do that kind of thing, because you need to have networks that have thousands, millions, billions, sometimes even trillions of nodes. That kind of computing technology would take a long time before it would become affordable and usable and affordable. So neurobiology is sort of creeping along under the radar. The more psychological or cognitive approaches to AI development were a little bit more public, but almost all of them, I don't think any of them stand out as resounding successes in the sense that anybody really believed that they didn't really seem to prove the idea that machines could think. Given their limitations that were provided by the hardware technology, together with the limitations in the cognitive approach itself. So I want to kind of jump ahead to the computing technology, the two big AI technologies that are in use now, and I'm going to do them in the order I'm doing them because one actually feeds into the other. I'm going to talk a little bit about machine learning, which probably was the kind of artificial intelligence which was having the most profound effect on us, the earliest, in the sense that machine learning, even if it wasn't openly visible to us, was happening in a lot of ways as early as the 1970s and into the 1980s, and has been very widely used in a lot of specific applications since then. But it also provided the foundation for what I think a lot of us think about when we think about AI, which is generative AI, or the ability of artificial intelligence, large language models to mimic human speech and apparently at some level human thought. So machine learning, how did we get there? It became apparent when the cognitive approach that we were talking about was not showing the kind of results with the kind of speed that I think folks would have expected given the advances in computer capability that were occurring, particularly in the 80s and the 90s. Trying to imagine how we think, work out how we think, and then model that in a computer was just a huge task. And writing that kind of computer code was very difficult and time-consuming. So the alternative to doing that, and once sufficient computing technology, once capable computing technology became available, it became clear that maybe the way to get computers to do more complex chores was in training them to do it, not programming them to do it, but training them to do it. And a great example of the difference between these two approaches is to look at chess computing. We all know what chess is. For years, computers got really, really good at chess, and the early chess computers worked basically by basically playing out almost every possible move at every stage of the game. The reason that computers were able to come up with astonishing moves sometimes is that at virtually every step of the game, when the computer took its turn, it was looking at every possible continuation, or virtually every possible continuation, and finding the one that it felt, according to an internal rating system, would provide the best result. Now, human chess masters kind of do this, but if you listen to them talk about it, they do spend some time thinking, if I do this, then you do this, then you do this, if I do this, like looking several moves ahead. But a lot of the chess masters will say that a lot of what they do is pattern recognition. In other words, by the time you played 10,000, 100,000 games, your mind has subconsciously memorized certain board configurations, and in a lot of cases, they're seeing those and saying, aha, this maps back to something that worked before. So when the second generation of chess machines, instead of trying to program the computer to do predictive analysis based on the current state of the chessboard, what they did was to feed a neural network thousands and thousands and thousands of chess games. And then once they had, in order to train it, and then once they had done that, they had people play against it, and then they had the computers play against themselves, right? And so in essence, instead of having to write a computer program that understood chess, what we did is we we created a chess program that, like us human players, was pretty lousy at it to start with. But over time and through training became an almost indomitable chess player. And for years, people thought that the Asian game of Go, which is another board strategy game, was something that artificial intelligence would never be able to conquer because it's just not, it's not approachable by the same kind of predictive analysis that chess, that chess was open to. But when they went and created a neural network essentially and fed it a whole bunch of Go games, and then had it start playing against human players, and then more importantly against other programmatic Go players, they got to a point where recently, now computers are beating human Go players, the best human Go players. So, it's a completely different approach to trying to mimic intelligence. And in a way, it's the most natural approach, right? Because we become intelligent by learning, by taking in data, by saying things, by being cross-checked by the people around us, by getting feedback on what we do. We hone our intelligence the same way that machine learning intelligences are honed. Although, with them it's done in a more systematic way. So it's a very natural model. And with the ability to have neural networks with millions or billions or maybe perhaps even trillions of nodes, you suddenly have the ability to create some very complex behaviors out of these large-scale training efforts. So machine learning, which is kind of the start of all this, you see, is the diagram visible to you? I didn't do it. I'm sorry. This is again a product of not having been up in front of real people in a real room, advancing real slides, real PowerPoint slides anyway. So machine learning, so neural networks. So a neuron basically, at its base level, a neuron is basically a thing that is connected to a bunch of other neurons. It receives input from neurons. It sends output to neurons. But the most important thing that it does is that internally it has a memory, right? And so some of the information that it gets is feedback on what it's done before. So when the neuron gets the inputs and it sends the outputs, at some point it gets some feedback from the system about whether or not, just to oversimplify, whether or not this is a good thing or a bad thing. And it takes note of that. And the more often that inputs flow through it and produces outputs, it will prefer certain patterns of output based on the feedback that it's been getting. But in base level, that's really what all of a neuron is. So a neural network is basically a huge network of these things. And you can see up there, the example up there shows what shows what a neural network that we might be teaching to recognize what a dog is might look like in a very simplified way. You'll see that each dot is connected, and it proceeds from the left to the right. So you'll see that each dot is, other than the first row, each dot is connected to all of the other neurons in the next level. And each one of those neurons will receive inputs from the level below it and send outputs to the level above it, all the time getting feedback from the overall system as to whether or not the outputs were useful or good according to some definition of what that is. And keep in mind that in the end, all we're really talking about here are numbers, right? They're probabilities. They're numbers between 0 and 1. So what we do when we want to train a neural network, I'm sorry, so what we do when we train a neural network, so in the case, we want to train a network to recognize a dog. So in the old cognitive kind of artificial intelligence, we would have written a program that said, okay, well, find something who's got 4 legs and a snout and maybe long ears, is covered with fur, right? But with with a neural network, what we do is we feed the neural network images of dogs, right? So we feed, so you'll see on the left, that's the input. The input going into the first column of neurons is essentially like sensory input coming from your brain. So it's so you take that image, you turn it into numbers, you feed those numbers into that first round of nodes in the neural network there, and each one of those will take the inputs that it receives, turn that into a number, and send that to each one of the outgoing paths you see going to the next level. And then the next level receives those, and each one of the neurons in that level receives their input from more than one source. They'll receive those inputs as numbers, and that neuron will determine, based on the numbers it receives from each one of those inputs, it'll define which neuron, which outputs it's going to send the neurons it's connected to on the next level up. And so, and through this process, you go through each level, and each level kind of further refining the representation of the image in the neural network until you get to the end. And we find maybe 1 million pictures of dogs. And we force those through the network, and each one that goes through leaves a trace. Because each one leaves a trace in those neural networks that is used and later passes through the neural network to bias the output, and bias the output in favor of having recognized a dog. Now, once we've done that, once we've given it say 1 million different pictures of dogs, then we start feeding it images that might have dogs in them, or might not. And in each one of those we run through, and at the end, the neural network will say, yes, that is a dog, or yes, there is a dog in that picture, or no, there isn't a dog in that picture. And then we'll look at that and say, was the neural network right? And if we humans say the neural network was right, then that feedback goes back into the neural network, and in essence sort of cements that result into the memories of the various neurons. If it's wrong, we say it's wrong. And we do that again, hundreds, millions, maybe even billions of times. And by the time that's all done, we have this huge network that is able to pick out or find or determine, to answer the question, is there a dog in this picture? And the most interesting thing in some ways about that is if you think that it's impossible to conceive of how the network determines a dog is a dog, it's not you. I mean, even the few people who design and build these networks can't tell you exactly how that happens. They can tell you mathematically how it happens on a case-by-case basis. What they can't tell you, though, is what's actually going on in the network, right? So those billions or trillions of nodes have learned from all of this training data that's been put into it. And all of that is contained in the neural network, and no person is able to really figure out how, for example, a particular picture is processed by the network to determine whether or not it includes a dog. I mean, it's a pretty miraculous thing. And it can be applied to, machine learning can be applied to almost any area in which you need to discern patterns out of a mass of data. I think most people are familiar with image data because those are the examples that are most often used. But in fact, anything that can be turned into, any kind of data that can be turned into a number or a group of numbers or a list of numbers, anything like that can be used to train a neural network. So neural networks can be trained to look for patterns in, say, banking transactions or stock trades or weather or consumer purchasing patterns. Anywhere where you have large amounts of discrete sample data that you can turn into numbers, those things are all good fodder for neural networks. And neural networks can become very powerful ways of detecting, of detecting particular patterns, particular kinds of patterns in very large, apparently random-looking collections of data. Face recognition is probably another one that almost everyone is familiar with. It's pretty remarkable pretty remarkable to look at how precise that technology has become, even in the last 10 years. given the availability of larger and larger and larger neural networks. Obviously, the larger the neural network, the more powerful it is, and the more powerful its ability to discriminate in this way. Another area I put on the slide, which I think is very interesting, is that if you're involved in a profession that involves your detecting patterns and things, and I chose medical imaging as being just one example I've read some recent stuff about. AI may be coming to do all or part of your job. Because one of the things that turns out that machine learning is very good at doing is taking X-rays, for example, large numbers of X-rays, and when you have a human feeding X-rays to the neural network, you feed the X-rays and you tell them which ones are of interest and which ones aren't. I mean, the neural network only understands that it is of interest or it isn't. It doesn't understand what the image is of, obviously. It turns out that some neural networks in some applications of medical imaging can be even more successful than humans at correctly identifying certain kinds of, tumors or other potential medical issues. So machine learning. Now, the interesting thing about machine learning, when I said that machine learning, anything you can turn into a number is fodder for machine learning, is fodder for neural networks. It turns out that words are like that too, words and sentences. So if you assign a number to every word in the English language, a sentence really is just a list of numbers of a certain length, right? And we'll, for the time being, toss out punctuation. And in mathematics, we call that list of numbers of a certain length a vector. And it turns out that neural networks are very good at dealing with vector kinds of data as well. When I was in college, I took a programming class where we had to do a project, and I did a project called, my project was a program called F-Wake, F-W-A-K-E, from Finnegan's Wake, from the James Joyce's novel. I've been taking a class on James Joyce, and we didn't read the entire Finnegan's Wake in one term, but we read a couple chapters of it at the end of the class. And the idea of the language of that book, if you've ever looked at it, really fascinated me. So I wrote a program that essentially took an electronic text of Finnegan's Wake. It created a list of all of the words and assigned a number to each word in Finnegan's Wake. And then I had it also, for each word, make a list of the words that immediately followed it anywhere in the text. Right, so you had the word "the," and I would have a list of all the words that followed it, along with how often each word followed it. So in essence, what I did was to try to recreate Finnegan's Wake once I'd built this table in the program, by starting with the first word of Finnegan's Wake, which is river run. And then, in essence, what the program did was to take river run, take that first word, look it up in my dictionary, so to speak, and then it looked at the words in the text that followed the word river run, and then it in essence threw it through a die, like computed a random number to determine which word would follow that one. Now it turns out river run appears only once in the book, so that was deterministic. But in the following words, each time it might have a list of 10 or 12 different words that might follow a particular word. It would choose one of those at random. So it would go through basically generating the next word in my synthesized Finnegan's Wake from the previous word. And again, I didn't do punctuation in that either, although a lot of Finnegan's Wake doesn't have much punctuation either. And it was kind of interesting. And then as the output, I had it produce about 6 pages of my own synthetic Finnegan's Wake. And honestly, I'll say that it didn't make a lot less sense than the original. Which is to say, it didn't make much sense at all. But so this whole idea of, and let me go on to the next slide here. I keep getting ahead of myself. So I say this. I've looked for 30 years for a context in which to use this quote. So forgive me if I'm taking up your time, but I finally found an opportunity to use it. It's Leonard Bernstein talking about Ludwig van Beethoven. He says, many composers have been able to write heavenly tunes in respectable fugues. Some composers can orchestrate the C major scale so that it sounds like a masterpiece, or fool with notes so that a harmonic novelty is achieved. But this is all mere dust. Nothing compared to the magic ingredients sought by them all, the inexplicable ability to know what the next note is. And that really is what generative AI or ChatGPT, there's the AI that we talk to now, that really is all generative AI boils down to, is computing what word comes next in exactly the same way that my Finnegan's Wake program did 40 years ago. So generative AI. The generative AI uses a huge neural network. In fact, one of the reasons that generative AI is so expensive is because the amount of power required to power a data center capable of building the neural networks the size of the neural networks used for ChatGPT, Claude, and some of the other AIs. It's almost inconceivably large. But basically with generative AI, it's very similar to what I just described to you. You basically start with a big neural network, and you basically feed it huge amounts of text. Now, while there are some large language models that are focused in particular areas of language, most of the really big, generally available ones use as their source of digitized text the one source the one place where you can get, billions, where you can get petabytes or billions of bytes of text, and that is the internet. So ChatGPT and the others basically mine the internet for any text they can get their hands on. And I'm sure you've seen some of the controversies over, what their use of copyrighted material, for example, or intellectual property might constitute as far as what AI produces once it's ingested all that, or what it means in essence for AI to ingest copyrighted content. But you feed it a huge sample of quote unquote meaningful text. And as you're doing that, you have the network generate its own text. And initially, the network, as with our dog example, initially the network will produce nonsense, will produce gibberish, will produce stuff that doesn't make sense. But they have specially designed feedback mechanisms that take that output and feed it back into the large language model and the neural network. And they do this over and over and over again to refine it. And after a while, again, as in the case with the chess computers and Go computers we talk about, they also have the AI itself start producing stuff that's fed back into itself. In computer science, we call it a recursive phenomenon, right? Where you take the output from something, turn around and feed it back into the same process. So that's called recursion. But that's what they do with the large language model. They begin with the internet, for example, as a source of text. They have the network generate text. They review the output. They feed the result. They feed the results back into the neural network or back into the large language model, along with feedback about how appropriate it was. And then, like I say at the bottom, rinse and repeat. This is done over and over and over and over again. And what you have is this gigantic network, which are essentially little dots with built-in probabilities, inputs and outputs that together in concert produce what appears to be a simulacrum of human speech and conversation. It really is kind of a miracle in the way it works. And all those years they spent trying to write programs based on the rules of grammar or the rules of syntax, none of that ever achieved the kind of success in normal kind of conversational rapport with the computer that the machine learning and generative AI has been able to produce. It really is kind of a miracle in a lot of ways. So there are a few problems with, there are some caveats, problems with the way AI produces its large language models, or generative AI produces the large language models. And these are just a few. Hallucinations is probably the best known one. the neural network doesn't know whether things are true or false. And in most cases, the training processes the training processes focus more on syntax, for lack of a better term, on form, than they do on content, which means that the feedback process doesn't necessarily include feedback on whether something is true or accurate. So hallucinations are when AI goes through, when you ask it a question and it goes through the huge mass of, of the network built on the huge mass of text that was used to produce it, and comes up with what it thinks is an appropriate response. But that response may not have anything to do with reality. One of the things that actually I encourage people to do, you probably noticed that when you do a Google search, for example, now, you don't just get the search results, the sites that you might be interested in, but you also get an AI summary at the top of at the top of your search screen. And what I oftentimes tell people to do is kind of an instructive exercise, because those AI summaries are very nicely worded, and I think that the fact that they're readable, they make sense, encourages people to believe that they're accurate, and they feel like they're accurate. They feel authoritative, and the fact they appear on your computer screen to some people gives them an additional air of authority, I suppose. But one of the things I encourage people to do is to do a search or ask an AI chatbot about something you really know a lot about. Something maybe you're a little bit expert in or aware of, or something you know of. And see whether or not the answer you get back is correct. When I put together this talk, I asked AI a couple of questions, and one of which was about look for some additional information about the 1956 Dartmouth Conference. And so the Google hits that I got below all went to information that turned out to be pretty good. Like one was a Wikipedia page, which is pretty informative and accurate. But the AI summary that it provided at the top got several things pretty fundamentally wrong about what came out of that conference, its conclusions, and even one of the participants. It had added a participant who hadn't been at the conference. So, I think it'd be worth your time to query AI about something you really know something about, and see whether or not the information you're getting back is accurate, even if you know that there's accurate information about that elsewhere, somewhere on the internet that you've seen. And hallucinations are especially dangerous in things like social media systems, where people don't often really think or stop to do the research to fact check whether something is true or false. I think there was a series of photographs that appeared that showed the musician Phil Collins, I think, being visited by various various famous musicians from his time, Robert Plant, Bob Dylan, Bruce Springsteen, I think. There were some photographs that showed up in my Facebook feed that showed him in a hospital bed being visited by these famous musicians from the 60s and 70s. And it occurred to me after I saw the third one that it didn't seem like Collins's expression had changed, or his position on the bed had changed. And it turned out, I did a little bit of Googling and searching. It turns out that those are viral AI-generated images out there that never happen. So hallucinations can be potentially dangerous, particularly in situations where people are inclined to want to believe or trust the social platforms and other news platforms that they are getting their information from. The second one I kind of mentioned, but it's I think kind of a bigger deal than it's going to be a bigger deal as time goes on, and that is intellectual property. You can imagine that going through 100,000 layers of a neural network, copyright probably doesn't get preserved anywhere in there. In fact, in many cases, the source of the information is completely obscured by the time you get into that. So, there have obviously been some public feuds over the use of AI's use of copyrighted content on sites like the New York Times and others. But now that we also, too, have chatbots that are producing things like like music and paintings. And you have to remember that those things are really, the principles that applied to generative AI for speech apply in exactly the same way to producing music and producing images. In fact, music is, as Leonard Bernstein told us a few slides ago, is actually ideally suited for that kind of what note comes next kind of analysis. And it's very easy for music to kind of appropriate ideas, concepts, whatever, from existing music and then produce quote unquote new music. In a way, music has had this issue through sampling since rap and hip hop became really popular, but I think it's coming into entirely new, into a new state with the emergence of generative AI. So I think we're going to be wrestling a lot with what it means to produce electronic content or intellectual content, what it means to own it, what fair use means. And while there have been some public examples, I think there's a lot more litigating, a lot more thinking that's going to go on in the next several years about what fair use means in the age of generative AI. There's GIGO, right? Garbage in, garbage out. So most of the chat bots that are in use now, as I said, are based largely on mining huge amounts of text from the public internet. And I don't know, in the early days of the public internet, I guess the early information superhighway, when the internet in the early 90s, when the internet was first getting some public visibility through AOL and some of the other online services, somebody made the comment, why are you surprised that 90% of what's on the internet is crap, 90% of everything is crap? But it begs the question, I mean, we're all familiar with I'll use a charitable term, with the variety of quality of content available on the internet. And knowing that the chatbots the chatbots probably don't distinguish deeply when it comes to quality from the material they're going to draw from. They're looking for the largest possible source of quote unquote sensible text that they can find. So don't be surprised when what you're getting out isn't that great or isn't true. I used Claude, the chatbot Claude. I've used it on a few occasions when I wanted to come up with, I've asked it to write sonnets for particular occasions because I thought, a sonnet's kind of a nice old-fashioned touch. So I have my sister-in-law is a hugely avid pickleball player. So I had Claude write me a sonnet on pickleball, a sonnet to pickleball. And I did the same thing for the Reston, I think I posted it on Facebook, but for the Reston cardboard regatta last year. And I did 7 or 8 of these, and I started realizing after I'd done 7 or 8 of them that they all kind of looked the same. I mean, not just the poetic structure, which obviously would be the same, but if you pick out any 2 Shakespeare sonnets, for example, you'll find a variety in sentence structure, these all seem to follow the same recipe in a way, both in meaning as well as in surface structure. So, and none of them were any good. I mean, they were amusing. Well, 2 of them weren't even amusing. And finally, I guess the last caveat I would throw out, which I've been hearing more about lately. I had a hard time figuring out how to talk about this. I call it lack of intentionality, but maybe the way to say it is that LLMs, chatbots, they don't have an agenda. They're not trying to do something other than getting you to continue the conversation, really. In other words, it's all about getting your input, because your input is what it needs to continue to build the network that it's used to create. I mean, that it uses to create and refine itself. So there's been some talk recently about the danger of teenagers using chatbots as sort of therapists. And honestly, the danger is that the chatbot, the LLM, knows nothing about what it is you're talking about. It's really in a way, it's all syntax with the illusion of semantics. Does that make sense? right? So it's all form with the illusion of meaning. And it's because the form is so skillful in creating plausible-looking form that we assume that it intends for the content to be there. But in fact, it doesn't know anything about the content. The form itself is what, its ability to provide the content is really its ability to provide form that looks like what I might say, or what you might say, or what somebody else might say when they make the same sort of comment. So the danger is that we have to keep in mind what AI is, what the chatbots are really up to. And they're not up to understanding you, except to the extent that understanding you makes them more able to get you to continue your conversation with them. AI doesn't, the LLMs don't understand the potential dangers or consequences of what they can say, because the consequences aren't ever really programmed into the large language models. So we have to be careful, because something that provides such an illusion of having intentionality, but really doesn't, is a potentially dangerous and possibly isolating thing, or isolated and potentially dangerous thing. And I think that's one of the things, as these chatbots start using voices, using vocal conversation, spoken conversation instead of written, I think that this is going to become even more challenging, and perhaps even the next step after that, which is having that speech coming from plausible-looking human faces. You can see where, psychology is poorly, I don't want to say that. The human mind and human emotions are an imperfectly enough understood thing from those of us who actually have them and use them, have brains and use them. To expect that machines will be any better at it is a fantasy, I think. So I'm just going to, I don't want to talk too much longer, but I do want to just kind of point to a few things. I think I'd like at some point, if you think this was informative, to maybe come and talk a little bit about some of the future directions of AI in a little bit more detail, and some of the kind of potential, both cultural and personal risks that at least I worry about. But for right now, I just want to kind of pitch out a few ideas that I had as I was putting together this presentation. First of all, you may have heard these terms before, but there really is kind of a progression in place right now from what we call AI to AGI to ACI. So AI is artificial intelligence in the small, artificial intelligence as it existed probably in the 70s, 80s, and 90s, where artificial intelligence was able to produce reasoning like behavior in certain limited contexts, like certain areas of mathematics or certain areas of science. And then to artificial general intelligence, which I think we're kind of easing into right now. The dream of McCarthy and his crew back in '56 was to have an artificial general intelligence. In other words, something that was able to understand that was able to understand and converse about almost anything, regardless of whether it had access to an internal knowledge base of that. I'd say one of the big differences with AI, between AI now and AI back in the 70s and 80s in particular, was a lot of that AI was actually drawing from databases of information and using the AI as a way to kind of mediate a conversation between the end user and the data source, whereas large language models really aren't doing that. There's not like a large database of medical information, for example, that they maintain, a vetted source of medical information they maintain when you ask ChatGPT like a health-related question. So artificial general intelligence, AGI, is an intelligence that is able to converse and learn in a more human way on a variety of different contexts and is not specialized in a particular area. And then there's artificial capable intelligence, and we're starting to kind of work our way toward that now. And that is when AI is given the ability to cross over into creating material effects in the material world. Now, it already does have effects on the material world in the sense that we humans ingest the output from AI in one way, shape, or form, and we do things on the basis of that, or we have computer systems that do things on the basis of that. But I think the next level is putting the AI in charge. So you have artificial general intelligence that's able to conceive of things that it wants to do, and then through various mechanisms is able to make those things happen in the real world. You know, whether it's control a nuclear facility or whether it's to direct traffic. And where this gets really, really interesting to me anyway is when artificial capable intelligence joins up with synthetic biology. Because we're now developing the ability to basically create new DNA. And DNA, like everything, it's just numbers, it's just code. You know, we have a concept, when we went from using physical computers at work to using computers in the cloud, the one biggest thing that changed is when I wanted to have a computer, I didn't have to call Dell and have them bring me a big box, right? All I had to do was give a few instructions to Amazon Web Services, to AWS, and they would create that. And once we realized we could do that, we realized that we could design whole computer systems, which would have required computers, physical computers before. We could create entire systems and store them as code, and then feed the code to AWS, to Amazon Web Services, and have it create the computers we wanted from the code. It's called infrastructure as code. And really, synthetic biology is kind of the same idea. DNA is just code. So there are systems that are evolving now that allow you to go from DNA potentially to producing actual organisms that are dictated, that are defined by that DNA. And so you add artificial intelligence and its ability to draw on this huge collection of connected information to, for example, do machine learning analysis of particular genetic combinations or DNA combinations, and develop and synthesize or imagine new combinations, that those could then be translated without human intervention into an actual living organism of some sort. I mean, it's a pretty astonishing thought, and while I don't think that particular thing is possible at this moment, I don't think it's all that far off. So the idea of artificial capable intelligence, and that to me is just the one single most amazing and probably frightening idea at the same time. Artificial and capable intelligence is one of those things that I think could have profound effects on not just on our culture, but maybe not even on our species as time goes on. So the next one I'm pointing to is cost, capability, asymmetry. That's a spaghetti word now that I read it. But what I'm really talking about is the fact that computing technologies, I'm sorry. I'm sorry. Oh, I didn't. I'm used to having this one control that one. So you're the one that says the future? Is that the one you're looking at? Okay, I'm sorry about that. So yeah, what I really mean by cost, capability, asymmetry is that it has been almost undeniable characteristic of computing technology that it starts out being really, really expensive and over time gets really, really cheap, and that this tends to happen really quickly. I mean, I remember going into Best Buy once, probably was in the 2000s, and buying a 1 gigabyte memory chip and reflecting that, 10 years earlier that would have cost $1 million, whereas I think I paid $32 for it or something. So it's what computing technology does, and AI is no different. So while right now you need huge data centers and huge amounts of power to create and use these LLMs, we recently saw an example in China where they're able to do something similar to what ChatGPT was able to do, but with substantially less expensive technical infrastructure beneath it. And I think as chips get better, as chips gets faster, as they're able to put more individual nodes onto a chip, as power consumption gets lower and lower and lower, we're going to find that these extremely powerful technologies are going to become less and less and less expensive, which from a consumer standpoint could be a good thing. I mean, Apple has an LLM that'll fit on your iPhone if you've got one. But it also means that really powerful technologies are available to almost anybody. And you talk about the ability to cross over into the real world in one way, shape, or form. What it does is to put very outsized capability in the hands of a lot of people. It puts, I think, potentially state-size levels of capability, of destructive capability, in the hands of much smaller groups and individuals. So technology in general, computing technology especially, but I think AI in particular, there is this asymmetry around cost versus capability that represents, I think we're going to see continue to grow as time goes on, and could also play out in some interesting and perhaps, unpleasant ways in the future. And then finally, the surveillance state. This probably kind of goes without saying, but the ability of these large neural networks to process huge amounts of communication data, for example. I think there was a time, for a time, I heard that there was a project where all of the phone conversations going over trunk lines in the United States passed through some CIA or some other owned facility. This was, I think, back in the late 90s, early 2000s, at a time when you really wouldn't be able to do anything more than the most rudimentary kind of analysis of what that traffic contained. But now, for example, doing something like that, it would be possible really to ingest that data and make use of it by using machine learning. So the ability of these large-scale neural networks to review huge amounts of visual data, auditory data, again, movement data, text data, whatever. The ability of those things to be able to create some sort of predictive sense out of, and to do recognition over these huge amounts of data creates an incredible opportunity, but incredible risk that the state can increase its degree of surveillance and knowledge of what we're doing. And actually, honestly, between you and me, I worry probably more about I worry more in some ways about business than I do about the government in that respect. I realize that the government may have more sinister intentions, but I think, the business itself has potentially more power and reach. And given that their purpose is to maximize profits, probably the strongest incentive to really exercise their use of that kind of surveillance in order to serve their own corporate ends. So the degree of surveillance that this kind of technology affords, I think, is something we need to be aware of. So last up, I'll finish up in just a minute. Oh, or you were just clapping for that thought. So finally, what can we do? What are some things we can do now? And I think most of it is around resisting the temptation to remain passive observers. I think part of the, it's easy because some of these things, when you read about them, even in the popular press, the language can get kind of tech heavy at times, and it can seem kind of overwhelming. But I think that we have to remember that this is emerging as a part of the world and culture we live in. And to the extent that we have any control of it at all, we only have it if we're aware and engage with what's going on. I think part of it is to become really thoughtful users of AI tools. Remember, it was once said to me in the early days of the commercial internet that if the site is free, the product is you, right? That what they're doing is they're giving you free access to the site in order to sell your data to somebody else. This is triply true with AI, which, as I said earlier, is using all of your interactions with the chatbots as ways to both continue to increase your own engagement as well as feed more data into the language model. And then finally, I think we have to demand transparency and accountability from companies, governments who are developing, promoting, and using AI. And I think this is the really big thing. And that's it. Thank you.
Thanks, Steve, and very much. It's a very important talk. Before anybody else asks a question, we've got time for one or two questions, but let me ask a question. This talk will be on YouTube, right, as are the other talks. And the question is, will AI listen to this talk, translate it, and be able to change what you say? Is AI now listening to YouTube talks and putting
Yes.
them into the system?
Oh, yeah, absolutely.
So that's a warning. Any questions you may ask, it's going to be in the cloud, whatever. And so we have,
Although it's, I mean, to be fair, it's not that some government bureaucrat someplace will know you asked the question. It will be that this will surface, this question will surface as part of the overall knowledge base that the LLM has when it's conversing with you. Of course, it'll only know it's me. It won't know it's you.
Carolyn has a question, right?
Just a comment that I heard. As AI generates more and more content that goes on the web, more and more of the content on the web will be AI generated. And the thought is, you know, people worry about AI taking over and becoming more intelligent than humans, but if it's feeding on its own output, nothing new, no new ideas are coming out.
Right. Well, I think you're exactly right. In fact, there's people talk about the AI singularity, and before somebody told me that what they meant by the AI singularity is when AI takes over, I always assumed that what it meant was if you have something feed on itself often enough, what you end up with is a singularity, with a circularity. And you're right. I mean, a large amounts of the data that AI is now consuming as content was produced by AI. And it probably answers maybe the question about quality. Like, can anything you've recycled be any better than the thing it was recycled from?
Tom, you have a question?
Yeah. Is anybody working on a large language model using French or Russian or Chinese?
I don't know about Chinese, but certainly all of the European languages. There are. I don't know if they're available publicly now, but they are working on.
You can
I
bet
think Chinese.
Chinese are doing-
I think Chinese and the ideographic languages provide maybe some challenges that the Romantic kind of languages don't. But there are active, all the European languages, there are active efforts, if there aren't products yet.
Dick?
Thank you. On the surveillance aspect, can predictive AI actually predict intentions or motivations of people that we're interested who are acting upon us?
So that's actually a really interesting question.
I'm sorry, I always have this problem with microphones. On the surveillance aspect, is it possible for predictive AI to actually predict intentions or motivations of people who we are concerned about?
So like I said, I think that's a really interesting question because, first of all, what the AI folks are pitching to their investors is the idea that the answer to that question is absolutely yes. So the investors who are looking at AI in terms of its commercial or financial prospects, one of the things that they're saying is that what AI will do is become able, based on all of these interactions, to predict what particular people are going to do under certain circumstances. And they're talking really in particular about, purchasing decisions of one sort or another. So I think that the belief is that having collected enough knowledge in general from the internet and having collected enough knowledge from you based on your use of the internet and maybe the conversations that you've had with the chatbot, that they will be able to make predictions about how much you might pay for an airline flight, or how much, or maybe even, I think they're already using AI to try to predict stock transformation, or stock futures, for example. So I think the answer to your question is yes. I think my own feeling, and again, I'm not an expert in AI per se, but my intuition would be that, an intuition is a prediction based solely on what people have done before is only part of the equation, right? And I don't know how AI gets beyond being more than that.
We have time for one more question. Greg?
Thank you, and thanks for the talk. a lot of technologists look at this field and look at facts as being fact, and they're always true. What is true, what is correct. But the cultural element, I think, is extremely important, and I'm not sure how we get at that. As an example, a large image of a large crowd in front of a government building with or without weapons prevalent. In autocratic societies, that would be, the presence of the weapons is what make everything okay. Whereas in most democratic societies, the presence of the weapons would be the indication of what's wrong. And I'm not sure how we get at that. I think it's part of the training. But it tells me that the right, if you will, answer, the correct answer, automatically generated, is really culturally based. Thank you.
Yeah.
Any comments?
Well, like as I said earlier, in a way, with ChatGPT, with generative AI, the question isn't what's right or what's wrong, it's what's next, right? And so what's next, whether it be a picture, whether it be a word, the next word in the sentence, whatever, it's all, again, based on the patterns that it has internalized in the course of the neural network, sucking up all of the text that it's gotten from the internet. So I think, it's interesting to me. I think we're getting to a point where representations are always going to be suspect, whether they're visual. It's funny, it amuses me a little bit that people still use what they call wet signatures, like a signature on paper, because it seems to me like maybe the least convincing proof, unless it was witnessed, it seems to me the least convincing proof that you approved of something. And I think that we're in a place where, unless there is a mechanism for us to, externally or independently validate the particular images are in fact the images that were produced from reality, versus those that were even subtly manipulated. And I'm not sure that you can, in this day and age, you can actually do that. This challenge of what's real and what's not is going to be, because it's so politically useful, especially. I'm not sure how we're going to have to wrestle with how we cope with that.
Okay, let's thank Stephen for a very fascinating talk.
Yeah, thank you. Thank you.